Good evening, everyone. Welcome to the problem solving session for the course Environmental Remediation of Contaminated Sites. So, this is the sixth problem solving session. So, we have covered 5 weeks till now. So, we have started with hazardous waste management, the rules associated with it, and then we have moved to risk identification of carcinogenic compounds and how to find out the hazard of non-carcinogenic compounds. And then we have moved to the treatment methods for the for the contaminated sites. So in that we have seen the first method as pump and treat, followed by permeable reactive barriers, and then we have seen a few numericals based on these methods, and then we have also seen a few case studies based on these methods, like where PRB was used to remediate one of the contaminated sites with uranium in US, and then in the from week 5, natural attenuation as one of the remediation techniques has been started. So we have seen a few basics about natural attenuation in week 5, and that thing is being followed in week 6. So in week 6 we have lectures for I think first two lectures are for the derivation of the formula, where there are two cases. First is where the contaminated contaminant is adsorbed on the soil sediments, where we have derived sir has derived the equation for that. And when along with adsorption, advection, in real life cases, along with adsorption there will be advection. So based on this scenario, a different equation was derived based on mass balance. So based on these concepts, I think third and fourth in the third and fourth lecture there was a numerical which was solved based on these derived equations, and the last lecture was based on a case study where natural attenuation was used. So let's go briefly through the lectures and then we will directly go to the questions. So let's go to lecture 26. So this was the first lecture. So here we have covered all these in week 5 on that. In natural attenuation, oxygen, if there is oxygen as the electron acceptor. Okay. So first let me share my screen. Okay, now my screen is visible. So in the previous week, we have seen that microbes prefer oxygen as the electron acceptor as compared to the other electron acceptors, because if there will be oxygen, then the energy, if generation with the oxygen as the electron acceptor is much higher as compared to other electron acceptors. So here from this table we can see if there will be nitrate. So this table shows the preference of the electron acceptors by the microbe. So nitrate and nitrite will be preferred more as compared to iron, and iron will be preferred more as compared to sulfate. So if we want to remediate a site which is contaminated with chlorinated hydrocarbons, then all of these above electron acceptors should not be present. So we will see a case based on this, that there in the last lecture that there is a contaminated site in uranium, contaminated site in US where natural attenuation was used, and we will see various operating conditions which was there in that aquifer. So again, there can be three mechanism. It can be aerobic or anaerobic or co-metabolism. So here from here the derivation of the formula based on adsorption and advection start. Please go through these derivations in the lecture video. So let me directly go to the final equation. So this equation was derived that Ct is equal to C naught e raised to power minus K dash T, where K dash T is uh, so K dash T is is K into R, where R is the retardation factor. K by R is the K dash. So this is a modified rate constant. So now let's go to lecture number 27. So here the equation is derived by considering both advection and adsorption. Here the final equation is dc by d tau is equal to minus k star into c. So tau is r, x is the distance from the center, u is the seepage velocity, and epsilon is the porosity. So we will solve questions based on both these two equations, and we will see there. So here it is also the continuation of that, and here a question was given based on these concept, and we will solve similar question in the assignment questions. So let's go skip these also. 20, lecture 28 and 29, these two are based on the numerical which was there, and let's finally go to lecture 30. So So this is a case study where natural attenuation was used for remediation of the site, which is located in Louisiana, USA. So this site was contaminated due to a non-aqueous phase liquid, which was the dense non-aqueous phase liquid. So the contaminants here was chlorinated ethene and ethane compounds. So uh, this is overall the site characterization, like what was where the site was located and what were the various uses of the nearby areas. So So there was the soil strata was divided into some part, like the site, the contaminated site was mainly clay, but near to that side there is a river, and in rivers the type of soil is nearly silty soil, so there will be porosity will be much higher, and since it is a river, so it will have some alluvial sand which will have very high hydraulic conductivity. So again, these are some of the data which is given. So this is the overall geochemical characteristics of the groundwater. So here we can see that dissolved methane was not detected. In fact, dissolved oxygen is not detected in the alluvium layer. So since oxygen is not present, so there the conditions is anoxic. And here we can see that dissolved hydrogen and inorganic carbon is present, and iron is also present. So hydrogen and iron can give electrons, and here other nitrate, these are also not present, and also if nitrate is present at very low concentration, sulfate and sulfide are also not present. So all these are the electron acceptors which are not present. So we have the chlorinated alkene, ethane and ethene. So that will accept the electrons, and that will through that these contaminants will be remediated by the microbes. So again, here a figure is shown which shows the different ways of exposure. So this area is the um, uh, so this was the clay area. So that's the way here we can see that the extent of the plume is not that much, but the area near to that is uh, alluvial clay and alluvial. So it will have clay, silt, and silt and sand will be in higher amount. That's why here we can see that the extent of the plume is much higher as compared to this layer. But since in the clay layer the extension of the plume is not that much, but from the adjacent layer it can be the chance that this plume will contaminate the this side with at greater that depth. So this was the chance, and also here it is a river which was Mississippi River near to the contaminated site. So here again, if the river will be contaminated, then it will be a very dangerous condition. So these were the contaminants and their corresponding concentration which was present. Here we can see that these are all are the chlorinated alkanes and alkenes, and also there are some benzene zincs also. So biodegradation assessment was done, and it was seen that cis-1,2-dichloroethene, which is a daughter product of chlorinated ethene and chlorinated ethene biotransformation, was present at concentration much greater than the concentration of other dichloroethene isomers. So in the aquifer already there were degradation of the contaminants which was taking place already, and the concentration of cis DC was below detectable level at other two monitoring location. So these was the case. So this site was remediated using natural attenuation. So we will see how the remediation was done in the next week lecture material. So now let's go to the question part. Okay. So this is the first question. So the question is, groundwater at a site was contaminated with trichloroethene, a halogenated solvent that has been used as a degreasing agent since the early 20th century. Samples were collected at four different locations in the direction of groundwater flow, starting from location A. Laboratory analysis data is given where the concentration of TCA at different location, all the four locations are given, and following observation were made in lab study. Analysis demonstrated the presence of cis-1,2-dichloroethene at location A, B, and C. Based on the above information, please select what can be the inferred. So, uh, concentration of TCA at the four locations is given, and also at A, B, and C, cis-1,2-dichloroethene was found out. So we have to select based on the given data which of the following statement is correct. So the first statement is natural attenuation of TC is probably taking place. B is attenuation due to adsorption onto soil is likely to occur. C, destructive attenuation of TC is taking place. D, TC is highly resistant to degradation. Or E, monitored natural attenuation cannot be used to treat sites contaminated with TCE. So I will give you 4 minutes. Just take your time and write the option which you think correct, which you think is correct in the chat box, and then we will discuss. Okay, let's see whether A, D, and E are the correct option or not. So we have been given four sites, and at the four different sites, the concentration of TC is given. So we can see that the concentration of TC is decreasing with the distance. So this is obvious also. So the first statement is natural attenuation of TC is probably taking place. So this statement is correct. So here we can see that in the statement it is given that the analysis demonstrated the presence of cis 1,2 dichloroethene at locations A, B, and C. And in the last lecture, we have seen that the TC during natural attenuation gets converted to cis 1,2 dichloroethene. So this is the daughter product of TC, and one more compound was given. So the first statement is correct. So the second statement is attenuation due to adsorption onto soil is likely to occur. So this is also correct. So because we can see that the concentration of TC has decreased, so there is chance that adsorption of the TCs on soil is taking place. Option C is destructive attenuation of TC is taking place. So this is also correct because here we can see that TCA has converted to cis 1,2 dichloroethene. So conversion of TC from one form to other form is taking place. So this is the destructive attenuation. So option C is also correct. So the fourth option is TC is highly resistant to degradation. So this is not correct. So because we here we can see that TC is converting to other components. So it can be degraded. And the last option, that monitored natural attenuation cannot be used to treat sites contaminated with TC. So this is also not correct because natural attenuation can be used to treat sites contaminated with TC because they can be degraded and they can be converted from more toxic form to lesser toxic form. So option A, B, and C, these three options are the correct option. A, B, and C. These three are the correct option. Now let's go to question number 2. Sorry. So the question is select the correct formula of rate constant for degradation of contaminant when adsorption is considered. Assume the rate of degradation follows first order. So based on first order rate constant rate of degradation, so we have to find out that out of the four formulas given, which formula is the correct for rate constant where only degradation is when only adsorption is taking place. There is no advection to be considered. So again, I will give you all 4 minutes. Just take your time, write the option in the chat box, and then we will discuss. Here we can see that for absorption, the final equation was dC by dt equals to minus k star c, where k star is k by r and r is the retardation factor. So on, sorry, so on integrating, so we are getting the final expression as k equals to r by t ln c naught by ct. So option A is correct. So B and C are not correct. A is the correct answer. So let's move to the next question. So the question is, in the Louisiana case study, select the reason for not considering pump and treat as an option for remediation. So why pump and treat was not considered for remediation? First option is absence of nitrates. B is anaerobic conditions. C is soil contained clay, or D presence of organic content. So again, I will give you all 4 minutes. Just take your time, write the option in the chat box, and then we will discuss. So in this case study, pump and treat method cannot be used. Sorry, because first the contaminant was a non-aqueous phase liquid, and there was a organic content which was present in the aquifers. So these any non-aqueous phase liquids, they can go and get soaked on these organic contents, and there will be tailing and rebound for very long period of time if pump and treat method is being used. So option D will be the correct option. So D is the correct answer. Now let's move to, so we will solve question number 4 and 5 at the end. So question number 6 is, what kind of soil is preferable as a layer above an aquifer to prevent contamination of aquifer? A. Pleistocene clay, B. Silt zone, C. Alluvium sand, or D. Permeable sand aquifer. So again I will give you all 4 minutes. Just take your time and write the option in the chat box. So A is the correct option. That Pleistocene clay layer is used as a preferable soil layer above an aquifer to prevent contamination of the aquifer because this clay because it has very less hydraulic conductivity. So because of that, whatever there is contamination in the water will not will seep at a very slow rate into the aquifer. That's why clay is used. Silt, alluvium sand, and permeable sand aquifers, they have very high hydraulic conductivity. So, in these, the contaminants will travel very fast. So that's why Pleistocene clay layer is used. So A is the correct answer. So let's move to the next question. So the question is, in the case study, what were the different mechanisms by which various environmental compartments could be polluted by NaPl, that is dense non-aqueous phase liquid? So first is infiltration and percolation. B is dispersion and inhalation. C is adsorption and direct contact ingestion, or D all of them. So in the case study, different mechanisms by which various environmental compartments can be polluted by DNAPL was given. So we have to find out what were the different mechanisms based on the options given. So again, I will give you all 4 minutes. Just take your time, write the option in the chat box. So D, that is all of them, is the correct option, because in the case study we have seen that the DNAPL can contaminate by either infiltration or percolation, or there can be dispersion of the contaminant, or people or animals can get uh, in contact by inhalation, or there can be absorption on the soil particles, and also there can be direct contact ingestion. So D is the correct answer. Now let's move to question number 8. So the question is, select the methods which cannot be used to see whether degradation is occurring or not. A. Historical data. B. By looking at byproducts and ORP. C. Microcosm studies. Or D. Standard cone penetration test. So we have to find out the method which cannot be used to see whether degradation is taking place or not. So the methods, that is historical, the data can also show whether degradation is taking place or not. And option B, by that is by looking at byproducts and ORP. So if some degradation is taking place and there are some byproducts, then by seeing at the byproducts we can say whether that compound is degrading or not, or and on the based on ORP, that is oxidation reduction potential, we can also predict the whether oxidizing or reducing the potential is in there in the aquifer, and based on that we can see whether we can say whether degradation will take place or not. And see, that is a microcosm study. So these studies are done in lab to predict the behavior of the some contaminant or microbes in present and behavior of microbes in presence of different operating conditions. So this method is also used to check whether degradation is occurring or not. And option D, that is standard cone penetration test. So this is done in geotechnical engineering. So so this is done to find out resistance, uh, measuring the resistance of the soil. So it can also be used to find out other properties of the soil. So standard cone penetration method is not used to see whether degradation is taking place or not. So D is not the correct answer. So D is not the correct method to find out degradation is taking place or not. So D is the correct answer. So now let's move to question number 9. So 9 is a numerical type question. So the question is, calculate the value of retardation factor if Darcy's velocity is one third of the seepage velocity. Bulk density is given, so that is 1750 kg per meter cube. We have organic partitioning coefficient is given, and the fraction of organic carbon is given, and we have to find out the retardation factor. So I think we have solved numericals based on retardation factor in, I think, week 3, where we have studied about the pump and treat method for the remediation of the contaminated site. Anyhow, the formula for the retardation factor was again seen in the week 6 lecture material. So again, I will give you all 5 minutes. Just take your time and try to solve this question. Everything is given. You just have to put these values in the retardation factor formula and calculate what will be the retardation factor. So please, everyone, please try to solve this question and write the value which you are getting in the chat box. Okay, let's see. So we have been given so Darcy's velocity is so there is a relation seepage velocity is given. Okay. So seepage velocity is given as Darcy's velocity divided by porosity. So we have been given the ratio of that Darcy's velocity is 1/3 of the seepage velocity. So Darcy's to seepage velocity will give us porosity. So porosity is, let's write Darcy's velocity as dV and divided by seepage velocity. And in question, thus Darcy's velocity is 1/3 of the seepage velocity divided by seepage velocity. So porosity is 1/3, that is 0.333. Now let's write the formula for retardation factor. Retardation factor is given as 1 plus bulk density into partitioning coefficient divided by porosity. So here bulk density is given as 1750 kg per meter cube, and partition coefficient is KOC, that is the organic partition coefficient into the organic fraction. So KOC is given as 210 ml per gram into partitioning fraction of the organic compound is 0.012. So let's multiply this. So it's coming out to be 2.52 ml per gram. If we convert it into liters per kg, so we do not need to do any conversion. So retardation factor now will be 1 plus bulk density is 1750 kg per meter cube. So let's convert it into kg per liter. So divide by 1000. So it will be 1.75 kg per liter. And Kp is 2.52 liter per kg. Divided by porosity is 0.33. So let's solve this and we will get the retardation factor. I think it's coming out to be 14.24. So 14.24 is the retardation factor. So I hope this question is clear. So if you have any doubt, then you can ask, or otherwise we can move to the next question. Okay, let's go to question number 10. Okay, so question number 10 is also a numerical type question. So we have to calculate the seepage velocity in meter per second. If porosity is zero point 0.3, hydraulic conductivity of soil is given and hydraulic gradient is given, and we have to find out the seepage velocity. So again, I will give you all 5 minutes. Please try to solve this question and write the value of seepage velocity which you are getting in the chat box. So 192 is not the correct answer. Let's see. So we have been given hydraulic conductivity and porosity with hydraulic gradient. And we have been given gradient. So hydraulic gradient is given. It is 50 mm per meter. So Darcy's velocity will be given as, so Darcy's velocity is given as Ki. So K is 5 into 10 raised power minus 4 kilometer per day. So let's convert it into meters. So multiply with 1000. It's per day. So in one day we have 24 hours. So 60 minute into 60 second. So it's meter per second.
Excuse me, madam. I have one question.
Yeah.
This is seepage velocity, right?
No, Darcy's velocity is given by Ki.
No, the question is calculate the seepage velocity.
So first we'll calculate the Darcy's velocity, and by dividing the
Uh,
Darcy's velocity with porosity, we will get the seepage velocity.
okay, okay, okay.
So hydraulic gradient is 50 mm per meter, so I'll convert into meter per meter. So 50 into 10 raised power minus 3. So it will be meter per meter. So let's solve this. So we are getting 2.89 into 10 raised power minus 7 meter per second. So this is the Darcy's velocity. So porosity is given as 0.3. So seepage velocity will be, it will be Darcy's velocity divided by porosity. So it's coming out to be 9.63. into 10 raised power minus 7 meter per second. So this is the required seepage velocity. So hydraulic conductivity and gradient was given. So from this we can find out the Darcy's velocity, and we can divide the Darcy's velocity by porosity to get the seepage velocity. So 9.63 into 10 raised power minus 7 meter per second is the seepage velocity. So I hope this question is clear to you all. So let's move to the next question. So the question is, the retardation depends on the porosity and bulk density of the aquifer. So we have to say whether that statement is true or false. So I'll give you all 2 minutes. Just take your time and write the option in the chat box. Sorry. So the retardation factor depends on porosity and bulk density. So this statement is correct. So we can also see from the formula for retardation factor, which is 1 plus Kb into rho b by epsilon, which is the porosity. So retardation factor is given as 1 plus Kb into rho b by epsilon. So this is the porosity and this is the bulk density. So retardation factors do depend on these two. So A is the correct answer. So now let's move to the two questions which we have left in between. So this is the question. We have an aquifer was contaminated with TCE and fuel hydrocarbons. Natural attenuation was chosen as the remediation action. Bulk density is given, porosity, permeability, hydraulic gradient, and the organic carbon fraction in aquifer material is given. And the organic carbon partitioning coefficient for, sorry, this is not PC, it will be TC, is given as 215 milliliter per gram. Assume initial conditions, assume initial concentration is constant, and we have to use Excel solver tool. So the question is estimate the actual first order rate constant using the following data considering only adsorption. So only we have to consider the adsorption. We have been given on different time intervals. We have been given the total TCE concentration, and we have to find out the actual first order rate constant. So let me directly go to the Excel, and then we will see how to solve this question. Okay. So this is the question given. So let's see how to. So here we can see. So I hope all of you know how to use the Excel solver. So first we'll find out the retardation factor here. So let's find out the K star, and then we will find out the retardation factor. So here I have written the time interval which is given in the question from 0 to 280, and then we have find out the total TC concentration which is given to that corresponding time interval. So next, so for adsorption, CT is given as C naught e raised to the power minus K star T. So we will assume any rate constant. So suppose I am assuming the rate constant to be 0.5. Okay. So here we will find out the concentration. So here we will write down the formula to find out the concentration. So concentration at any time t is C naught. So let us assume CT initial to be 950. So I have assumed CT as 950. So concentration at any time t will be C naught, which is this one, C naught into e to the power minus k we have assumed as 0.5 into t, which is 0. So we will put this CT initial and K star into dollars because this will be same for all the condition, and then we will find for all the time interval which is given. So this is the value which we are given. So then we will find out the error. So error will be nothing, but it will be the difference of the true value and the model value which we are getting. So this is the difference we are getting, and then we will find out the square of the error. So square of the error we have find out, which is nothing, error raised to the power of 2. So then we can find out the square of the error, and finally we will find out sum of square of the error. So we have find out the sum. This is nothing but sum of the square of the errors. So this is the sum. Now what we have to do, we have to minimize the sum of the square of the errors using solver function by changing the rate constant k. So let's go there. So we have to go to solver. So in the data we can see solver. So our objective function here is this. We have to minimize the sum of the square of the errors. We have to minimize this by changing the variables. We will change both rate constant and CT initial. So now next solve. So the solver has solved. So we will keep the solver solution. So we can see here that K star has changed from 0.5 to 0.008097. So this is the value of K star. Now we have to find out the actual rate constant, which is nothing, which is K star into R, where R is the retardation factor. So now let's find out the retardation factor. So I have calculated it somewhere else. So we can find out retardation factor. So let's see what is given. We have organic fraction is given as 0.022. We have KOC is given as organic carbon partition coefficient is 215. This is ml per gram. And we have bulk density as bulk density is 1650 kg per meter cube. So, okay, so R is given as 1 plus, we have been, yeah, KB is nothing which will, okay, so we have to write first porosity. Porosity is given as, I think, zero point 0.3. Okay, porosity is 0.3. So we can find out the retardation factor as 1 plus KB. KB is nothing, it is FOC into KOC, and then it will be multiplied by bulk density. So to convert the bulk density into kg per meter cube to kg per liter, so we will divide by 1000. So let's do it. 0.001 divided by porosity is 0.3. So we are getting the retardation factor as 27.015. So this is the retardation factor which we are getting. So we can find out actual K using this relation, that actual K is K star into retardation factor. So our K star is this into retardation factor we are getting is this. So the actual K is we are getting is 0.22. So the correct answer here is K is nothing, it is 0.22. So this is the value which we are getting. So now let's move to the second part for this question. So this is the question number 5. So the question statement is same. So we have to find from the data from above estimate the actual first order rate constant considering both advection and adsorption with the assumption of plug flow. So we have to find out considering both advection and adsorption, we have to find out the rate constant. So here the aqueous TC concentration with distance is given. So initial distance is 0 and the TC concentration is 950. So let's see how to solve this question. So here and the question statement is that we have to find out the rate constant in per year. So we will do the calculation according to that. So what I have done, I have written the distance and the corresponding aqueous concentration is being written, and tau is given as xr, where x is the distance, r is the retardation factor, and u dash is the seepage velocity. So from the question we can find out the retardation factor which we have found in the previous question also. So in the question permeability is given, it is 0.9 10 raised to power minus 4 is the permeability. So this is the permeability. So permeability is given. Next we have gradient. Gradient is given as 0.09 meter per meter. Next we have given Darcy's velocity. So Darcy's velocity is given as, so Darcy's velocity will be given as K into I, that is permeability into gradient. So permeability is this much and gradient is this much. So we got the Darcy's velocity and we can find out the seepage velocity by dividing the Darcy's velocity by porosity. So we have this much of Darcy's velocity divided by porosity is 0.3. So, sorry. So we got the seepage velocity. So now we can find out tau. Tau is x. X is 0 here. Into retardation factor is 27.05 divided by u dash, that is the seepage velocity. So I have written the formula here. We will put the seepage velocity and r into dollar sign because this is same for all the x values. So we can drag it and we can get the required tau values. Now, as when advection and adsorption is considered, then the equation is, so this is the expression and tau is the function of x, which we have seen tau is equals to x r by seepage velocity. So first we'll find out k star, and k star is nothing. K star is k by retardation factor. Okay. So now we can find out the concentration at any time t. So we have assumed the initial concentration as 982. So here the initial concentration will be nothing. It will be T10, that is C naught e raised to the power minus K. K we can assume from here. Suppose we have assumed it as 0.5. 0.5 divided by, we will divide it by 365 into 24 into 3600 because we have to find out the K into per year. That's why we are dividing it with this value because it is generally in per second. So in 1 year there will be 365 days and in each day there will be 24 hours and this much of seconds. So that's why we have done that and we can drag this and we can find out the initial concentration at all the distances given. Next again we have to find out the error. So error will be nothing. It will be the difference between the model value which we have got and the aqueous TC concentration. So it will be 982 minus aqueous square TC concentration. So this we can drag here. We can get the error. And next we have to find out the square of the error. So square of the error is 32 raised to the power of 2. So then we can drag here. We will get the square of the error and then we will find sum of square of the error. So this is sum of the square of the error. Now we have to use the solver. So let's go to data, then solver. So we have to minimize. So our objective function is we have to minimize the sum of the square of the error. So we have to minimize it, and by changing the value of rate constant. So if we will solve this, we are getting the rate constant as 1.77, and we can find out actual k by dividing this k, that is 1.77 divided by the retardation factor, I think. Sorry, this will not division, this will multiplication. Actual k will be uh, r into k star. So where r is 27.015 into k star is this much. So we are getting 47.80 as the actual rate constant k. So this is the final answer which we are getting. So the actual rate constant is 47.80. So I hope these questions are clear to you. If you have any doubt in these two questions or in any of the before solve question, you can just unmute yourself. You can ask. We can discuss these questions.
So,
Yes. Okay, I think there are no questions then. So these were the
problem
questions. Sorry?
comes from the Excel. So, any special thing is to be done in the Excel, or just use the Excel sheet?
When you have to use the Excel, sir? I'm not getting the question.
So, I'm saying that for this question, calculation of this data,
Huh?
so the Excel sheet is to be made by us.
Yeah, you
Uh,
have to make the Excel sheet, and then you have to use the solver function to find out the K star values.
yeah,
Okay. Okay, I think there is no other doubt. Then
right.
so
Thank you.
okay, okay. Thank you so much for joining. We can end the session here. So we will meet on next Sunday on the same time, that is from 6 to 8 p.m. So have a nice day. Thank you. Okay, thank you. Thank you so much.